But we are now recording. Let's go from the current slide. And before we get to that slide, though, I wanted to have to do this before I turn on the recorder here. I think I've got actually about two people not shown, so that can have. Okay. Now, there's probably some other announcements I should be making, as in how tardy some people are, but good to see you. And please see me before you leave today, okay? I barely had time, but I did get it done this morning to print off this one. Like I said, there's probably some other announcements I need to be making, but this one's right near the top of the list, so I got to print it off. Are any of you familiar with a program called NOYCE Scholarship Program? It's N-O-Y-C-E. What it is, and it's different schools probably handle it slightly differently, but evidently Alabama A&M University has now launched a AMU NOYCE scholarship, and they have a website. So if any of you are interested, go to that website. Lawson State is a partner on this scholarship program. Now, I don't know who the contact person is. This came from Dr. Crawford, our Vice President for Academic Affairs, or Instruction, Vice President of Instruction. And I know he used to be at Alabama A&M, so it may be that he's our contact person, okay? There is a link, and what I advise you to do is go check your email, because it was sent to all students at Lawson, all students at studentslawson.edu. So you should be able to catch it there. I haven't looked at it myself, so I can't tell you any details, but you can read those. What the other NOYCE programs that I've heard about, UAB had one and Tuscaloosa had one. I don't know if theirs are still up, because they're usually 3 to 5 year grants, so if the grant's expired, they may not be doing it anymore. But they have typically been trying to encourage students to consider teaching. And so if you're in a math-related major, which all of you are, engineering or whatever, math-related, or science-related, they would encourage you to participate in this to see if you might have an interest in teaching at some point. So that may not be what Alabama A&M's is focusing on, but that's what the other two have been. So check it out. If I remember correctly, the other two were very lucrative for the students. You only had to do like 3 to 5 or 6 weeks or something like that in the summer. They paid you. They paid your room and board. They covered expenses there and back one time. It was a very nice program. And I actually had some students who continued taking courses here and did it through watching, YouTube videos and things like that. So it doesn't preclude you from taking, your regular load here, but you can still do that perhaps if you can work it out. So please give that a shot. Check your email. You'll find it there. Okay. Dr. Crawford is the author of that email, so don't ignore it. Pay attention to it. Okay. Where we left off last time was example 9, bottom half of page 116, chapter 2, differentiation, 2.2, basic differentiation rules and rates of change. And 9 is dealing with the rate of change problem. Any questions on anything before we get going on this? And just wanted to mention, this class has been a bit behind, in fact, quite a bit behind most of my other classes in getting research papers in, as in 0 out of my best class ever, of course, okay? And so please don't forget about those. Month of February, you still get 3 bonus points. January's fourth bonus point, that's all history now, so please. What's that?
You said turn the papers in or the topic?
The papers can be turned in any time. Yeah, the topics you may have already turned in, but I need the paper to give you your bonus points. Okay. So anytime you can, get those papers into me. Also, first test. I think 1, 2, 3, 4, 6 of you have turned in first test already, which is great. The rest of you, please, I hope you're working on them. You've still got time if you need to take it. Okay. Any questions? All right. Now, I've heard a few of you say you were having trouble on certain problems and stuff. Remember, I won't work a problem. I'll try to explain a problem from the test, but I won't work one, find one similar to it in the text. I'll be glad to work anything from the text, as long as it's not exactly the same problem. Okay. So no questions? All right, here's example 9. A billiard ball is dropped from a height of 100 feet. I think we started this last time, but ran out of time. The ball's height at any time s, at any time t, is the position function, and I told you where this came from. The minus is because gravity always pulling the ball downward, and downward it's counted negative. You started, though, 100 feet up from your 0 reference level, so that's where the 100 came, plus 100 came from. But the acceleration down is downward, so that's going to drag it downward. The 16 came from 1/2 of the acceleration due to gravity. In the U.S. customary system, feet in seconds. Distance measured in feet and time in seconds. The acceleration due to gravity is negative 32 feet per second squared. 1/2 of that is negative 16 feet per second squared. And hopefully before the end of the term, you'll know why the 1/2 is in front. You don't have to know that yet. Integration constant, by the way. But you'll know it by the end of hopefully this term or early next term. Okay, find the average velocity over each of the following time intervals. So this is asking for average velocity, not instantaneous, but average. So how would you do that? What is the average velocity? There is Cedric, right? Okay. All right, good deal. Anyone else come in since I called roll and I'm going to see? How would you do this? Average velocity. How would we define average velocity? Or any velocity? Okay. Second. Distance over time. Excellent. Okay. Now, how would you find the distance? These are, by the way, what? 1 and 2. What does that represent? Time intervals. Exactly. So these are times. Times in seconds. So this is from 1 second to 2 seconds. So if you're doing distance over time, what do we mean by that? With this in mind. What would be your distance? The position function at time 2 minus position function at time 1, that would be the distance traveled, right? Position then minus position now, that would be the distance traveled, divided by what? Difference in time, which would be 1 second, right? So, basically what this would be, let me get my pen set up. Okay. Your average velocity would be change of displacement over change in time. The delta stands for change, right? Funny little symbol, okay? So this would be S of 2 minus S of 1, that's your change of position, which is the distance traveled, divided by 2 minus 1, which we'll work on that. Pull out your calculators, okay? Now, what is S of 2? Want to plug it in, or can you do it in your head? Perfect. Second?
36.
30. What'd you say?
36.
32 or 6? I can't hear well. Huh?
I said 36.
36. Okay, let's see. We had 2 squared is 4 times 16. 4 times 16. Okay. That's negative plus 100. You say 36. Okay. Minus. What's S of 1? It'll come back. Yeah. For some reason, when I twist this, somehow it shuts off. Okay. S of 1, what would that be?
84.
84. That's sort of, all right. Okay, that's okay. That looks sort of bad because it's going to be negative. Is that okay? Why? It's going down, exactly. And the velocity has to be downward. So yeah, we expect a negative velocity. Negative acceleration, wasn't it? Okay, and anyone work that out on your calculator yet? 1, I did. Okay, you didn't have to pick that up. Okay, and what's the difference between 36 and 84? Second? 48. And what would that be in? Second? Feet per second. That would be your average velocity minus 48 feet per second. Okay? All right. Yes, gotcha. I'm just trying to find you. I know you're in here. Quit trying to hide. There you are. Got it. Anyone else come in since the call roll? Okay. Now, let's get a little bit tighter here. The average velocity between 1 and 1.5 seconds. Now, the only difference here is which? Your S of 1.5. Now, this one, I think I probably would come close to needing a calculator on. 1.5 squared, I think, is 2.25. Is that right? Times 16. Oh, too early on a Monday morning to do that one in my head.
36.
Huh?
36?
It may be. No, it's 36 last time. It better not be this time. Okay. Okay. It is legal to use calculators. I know early. Huh? Pull them out. Crank them up. Okay. I know it would be 32 and 8, 40, no, 40. Is that right?
64.
64? Oh, after you subtracted, right?
S of 1.5.
S of 1.5 is 64. Minus 84. Okay, that sounds reasonable. And what would that be? 20. So this one would be 20. Negative 20 feet per second. Okay? How about from 1 to 1.1 seconds? Oh, wait. You didn't divide by 0.5. What would that be? Now, that one shouldn't need a calculator.
40.
Negative 40 feet per second, right? Okay. How about 1 to 1.1? We already got the 1 done. What would be your 1.1? S of 1.1. It's 1.21. 16. Yeah, I'm not going to do that one in my head. What's that?
I think the answer is negative 33.6.
At the very bottom. Divided and everything, right?
Yes.
Okay. Negative 33.6. Is that what you said? 33.6. Anyone else come close to that? And that would also be in feet per second. All right. So it does look like we're following the pattern here. These are getting a little less negative, meaning a little more positive, as you got closer and closer, meaning the slopes here were, they were negative, but becoming a little less negative, okay? All right. Does anyone want to hazard a guess what the instantaneous velocity would be? And how you would get that? I don't think the problem asked for it.
Is velocity the derivative
Of displacement, exactly. Okay. And what would be the derivative of this? We'll call it S prime is equal to negative 32 t. And since we're going closer and closer to 1 second, this would be negative 32 feet per second. Because this 32, that 16 is in feet per second squared. Multiply it by second, you get feet per second. Yes, and those were getting progressively closer to minus 32 feet per second. So I feel nice and warm and fuzzy that those are the correct answers. Plus the fact they got them in the book. That makes me feel even nicer and warmer and fuzzier. Okay. Make sense?
What did you just say?
Oh, the one up there? Okay, we took a derivative of this.
Oh.
That's, and by the way, that is ds dt. Maybe I should have written that. That probably would have been a good instructive thing to do. Because down here, it was delta s's and delta t's, right? And as the deltas get smaller and smaller and smaller, they go to becoming ds dt. That's where that notation should ring a bell. Whether that's what, I think it's what Leibniz intended, but whether he did or not, it's a good way to look at it, okay? The S prime doesn't really tell you that much. It's shorter to right, which I like, but the S dt would then be the derivative of that. 32t, plugging in for t equal 1, because we're getting closer and closer to 1 second. And sure enough, that would have been minus 32 feet per second. Make sense? Okay, good deal. All right. And let's see, do they even show a figure for this? Let's see if they do. Okay, here's how they do it. For the interval 1 to 2 seconds, the object falls from a height of s equal 1 of 84 feet to a height of 2 seconds, 36 feet. So the change of height would be your minus 48. It's always S2 minus S1, okay? Final minus initial, or whichever came second, whichever came first, okay? And that was minus 48 feet per second, because you were exactly 1 second apart. And then for the second interval, all we have to do is figure out S of 1.5, which was, after much wrangling, 64 feet. And you subtract 64 minus 82, came down to, but then you divide by 0.5, and that gave you minus 40 feet per second. And then the last one, all we had to do was figure S of 1.1, which would give you 80.64 feet. Subtract from that 84 minus 33.6 divided by 0.1, which is your time interval, and you came up with minus 33.6 feet per second. Okay? Note that the average velocities are negative, indicating the object is moving downward. On Earth, we usually have things falling downward. And also, it appears that there could be a limit to this, and indeed it is this. So in general, S is equal to S of t, position function of an object moving along a straight line and dropping a thing as it falls. No Coriolis effect going into play here. It's just too short a distance, so we don't have any twisting because of the Earth's spin or anything like that. Then the position function for an object moving along a straight line. The velocity of the object at any time t is the limit as the delta t approaches 0 as S of t plus delta t minus S of t That gives you your change of displacement over your delta t, change of time, and that's the same as s prime, or, you know, in this case, ds dt. That would make a lot of sense here. Change of s over change of time. Delta s over delta t, ds dt. In other words, the velocity function is a derivative of the position function. What Dawson was asking, velocity can be negative, 0, or positive. Okay? The speed of an object is the absolute value of its velocity. Velocity is a vector quantity. If you think of this, velocity vector, speed scalar. The speed is always absolute value. You never have a negative speed, but your velocity could be negative depending on, well, just like this, moving downward. Okay. Speed cannot be negative. It's a scalar quantity. But again, that's getting into physics stuff, which, believe it or not, calculus is closely related to. Okay. The position function of a freely falling object, neglecting air resistance, okay, big caveat here, under the influence of gravity can be represented by the equation S of t is equal, oh, there it is, negative 1/2 gt squared plus v0 t plus s0. I didn't know they were going to give us the actual physics formula. Okay? And again, minus 1/2 g being in the SI system, 9.80 meters per second squared, in the US customary, 32 feet per second squared. The acceleration due to gravity. And 1/2 of that, that's where we got our 16, negative 16. Our initial velocity was 0 because we dropped it. We didn't throw it. Okay? If we had thrown it, initial velocity would have been something different. Okay? We had even thrown it up if we had an upset stomach. No, never mind. But that would have been that. Or in the S0, that was our 100. That's where we started from, right? Wherever we started. Okay. That's your position function in the most generic form. This is no air resistance, under the influence of gravity alone. And that's what free fall means, under the influence of gravity alone. Okay. So where S of 0 is the initial height of the object, v0 is the initial velocity, and our example was 0, g is acceleration due to gravity. As long as you're on the Earth, on the surface of the Earth doing this, then that g will be constant. Okay, go to the moon or someplace like that, yeah, g will change. Okay. On Earth, the value of g is approximately 32 feet per second. I like to call it feet per second squared. It's easier to write than per second, and easier to say too. Or 9.8 meters per second, or 9.8 meters per second squared. All right. Any question? All right. Any of you taking your physics yet? Or some of you taking it now? Okay, good. You probably old hat to you, right? Good deal. All right, example 10. Hey, they even have this one in here. At time t equals 0 seconds, a diver jumps from a platform diving board that is 32 feet above the water. Not me. Okay. Here's the figure. That's not me either. Okay. The initial velocity of the capital velocity here, that must be important. The initial velocity of the diver is 16 feet per second. Now, what do you notice about that?
Positive.
Positive, meaning he's jumping up, or she's, yeah, he, hope so, is jumping up. Okay? When does the diver hit the water? Just before, when this flashes, okay. So how do we find that? When does the diver hit the water? What would be your guess? Hint. Okay, write down the equation. S of t is equal to, anyone remember what it was? Hint. Got it? Negative 1/2 gt squared plus V0T plus S0. Okay? Now, any of these things we know have a clue on what they are? What's that? V0? What's your V0? Okay. Okay. T0, is that what you said? No. Okay. I'm not hearing well. Say it one more time. T equals 0. Okay, when T is equal to 0. Okay. That's when we're starting. When T equals 0, the diver jumps. Okay? And when what we're looking for is when does it hit the water, so we're going to be looking at T final. That's going to be our T initial. We're going to be looking for T final. That's going to answer this question. Okay? So we need to fill in as many of the other things as we can, because we know at T equals 0, well, what do we know right now? T is equal to 0, that would be 0, that would be 0. What would your distance be? 32 feet. Okay, so we know that the 32 feet is our S0, right? That's our S sub 0, initial displacement. Because there it is. He was standing right here before he jumped, so his initial height was 32 feet. Okay? What else do we know?
The initial velocity.
Oh, and what is his initial velocity? And what is that in our formula down there? That's your V sub 0. Right when he jumped, he was moving upward. Sounds like a pretty good jump to me. 16 feet per second. Okay? Of course, he doesn't jump up 16 feet because gravity's pulling him down from the moment it's always pulling him down. Okay? So that's our V sub 0. And for some reason, that's not showing up well on my projector. Okay? It's V sub 0. Anything else we know from here?
G.
Second?
We know G.
Oh, and what's G?
30. 32.
Okay, this is 32 feet per second squared. Okay? And we usually use that, since we have the negative in the formula, we use G being positive. Okay? One more thing we know. When does he hit the water? What's going to be his, what two things are going to be true? Well,
After he goes 32 feet.
okay. After he goes down 32 feet, well, what will be his height then? 0. So this is going to be 0. I think we can do it now, folks. 0 is equal to, I'll do half of 32, negative 1/2 of that. That's negative 16, I think. T squared plus 16t plus 32. That looks like our equation that's going to tell us when he hits the water. At what time will he hit the water? Any of you want to tackle solving that equation? There's no calculus involved. Sorry about that. What would be your first step to solve that equation?
Pull out 16.
Second?
Pull out 16.
Okay, pull it out. Okay. What do you mean by that?
Raise common factor.
Second?
Pull out 16 and factor it.
Okay. I'm going to raise you one. I'm going to pull out or factor out a minus 16, because I don't like leading off with a minus sign. And what will that lead us with? T squared minus T, is that what you said? Okay.
Minus 2.
Minus 2. Okay. Now, what would you do next?
Factor.
Okay, I like the idea. And how will that factor? Okay, a little louder. See, T minus 2, T plus 1, is that what you said?
Yes, sir.
All right, good deal. Okay. And the minus 16 is still there, I take it. And that's equal to 0. Now, divide by what? Divide by negative 16. I will buy that as well, because it's not 0. You can divide that anytime. Divide 0 by negative 16, and what do you get? 0. Okay, we got rid of the negative 16. Or we could have said 3 factors multiplied to be 0. One of those has to be 0, right? Can negative 16 ever be 0? No. Okay, so throw it out. Okay, it's not part of our solution. It is part of the factoring, but not. So what are 2 possible solutions? T equal 2 seconds, or T is equal to negative 1 second, because T is in seconds. Okay, how many of you have ever jumped from negative, or do you think he's going to land 1 second before he jumped? Any of you? I want to see it. Okay. Actually, what that means is he would have jumped from down here in order to catch himself there, at 0 seconds. That would have been right. Okay, but he didn't. Okay, I guarantee that. Okay, so we throw out the negative 1 second since none of us have ever landed before we jumped, and we'll say 2 seconds after he jumped. Okay, good deal. And just for your cultural enlightenment, that first second, for the first half second, he was on his way up, the second half second down, and then the last second, he was hitting the water. Okay. He was picking up speed very quickly then. Okay. Anyone want to? Okay. So that answers our first question. T is equal to 2 seconds. Everybody see it? Now, what is a diver's velocity? Is impact. Okay. I think I need to erase some stuff so I can write in here. Is that all right to erase? Everybody got it? Yeah or nay? Okay. So let me erase some of this. There's some parts I'm not going to erase, and there is a reason for that, believe it or not. Okay. I knew I was going to do that. Okay. So what is a velocity impact? What would be your guess?
Plug 2 into T.
Say again?
Plug 2 into T.
Okay.
Plug 2 into T.
First what?
Plug 2 into T.
Plus. Oh, plug 2 into T. Okay, is that what you said? Got it. What would that give you? It's displacement at impact. What's that? Oh, yeah. A good Jesus answer, right? Take a derivative, okay? Take a derivative of this. That will give you velocity at impact. So what is, yuck. Still have this on. Let me take it off. Say again. ds dt is equal to, oh, I should have left that last part in. But yeah, what do we get? Negative 32t, perfect, plus, and V0 was 16. How about the S0? Huh? Yes, the derivative of a constant is 0. Okay, now, and this, by the way, is also a function of time. So what do we do here? Now's your turn. Plug in the 2. Okay, so the ds dt, which is velocity, let's just call it v of t, is equal to v of 2, 2 seconds later, would be what? Negative 64 plus 16, and that would equal 48 what? Feet per second. Because remember here, this was 32 feet per second squared here, times second, 2 seconds, that would give you feet per second. This was already 16 feet per second, so minus 32 feet per, 64 feet per second, plus 16 feet per second, 48 feet per second. Okay, and it should be negative. Perfect. Because he's going downward. No matter how much you may be scared to hit that water. at that speed. That's going along pretty well. If you've ever watched the divers, platform divers on Olympics and things like this, is that coming up next summer, I guess, okay? You'll notice they're always disturbing the water. They have water going in. Two reasons for that. Water has an incredible surface tension. Those hydrogen bonding between the H's on the water and the O's on the next water molecules are really, really strong. And if you were to go into that, have any of you ever done a belly flop? Okay, even from a slow dive, that can hurt, okay? So from 32, when he's going at that kind of speed, that would cause some probably serious damage. Besides just hurting you, making your stomach all red, that would be. In fact, some people have actually jammed, if not broken, fingers if the water is not disturbed. Disturbing the water breaks up that surface tension. The other thing it does, it gives them a better idea. Otherwise, it's a mirror, and he can't see where the surface is. That gives a little bit of, coming at that speed, though, I don't know how he sees it anyway. But anyway, that's what they do there, because that's going pretty fast, okay? And 32 feet is about 3 meters, right? No, wait. About 10 meters. About 10 meters. So this would be a 10-meter board. Okay. Do they do 10s and 5s or 5s and 10s and 20s? I don't remember. But they get way up there. That's not me. Okay. Let's see how they do it. That's how we did the problem. Let's see how they do. Begin by writing the equation, good for you, to represent the position of the diver using the position function given above. G was 32 feet per second, or feet per second squared. V0 is 16 feet per second. S0 was 32 feet. Then this was our formula. Just as you did it. Okay? And just as you saw, that became negative 16t squared plus 16t plus 32. This is negative because acceleration is downward. This is positive because he jumped up. And this was positive because he started from above the pool, which is a good place to start. To find the time when the diver hits the water, that means he's reached that level where S is equal to 0. So plug that in for S and solve for T. And just as y'all did, you pulled out the minus 16 and then factored what was left and got T plus 1 times T minus 2. And plugging that in, that gave you either time of minus 1 second, which was before he climbed up there, or 2 seconds later. I believe we'll go with the T equal 2. Because T has to be greater than or equal to 0. Choose the positive value. Conclude the diver hits the water 2 seconds after he jumped. Okay? And the velocity at that time would then be the derivative, the S dt, which is minus 32t plus 16. Plugging it in, just like the lathe, you would get minus 48 feet per second. Make sense? Good deal. Oh, notice that the unit for S of t is the unit for S, feet, divided by the t. Just think of this. That's why ds dt is a little bit better here. S over t. Distance per time. Feet per second. Okay? It's the F divided by the unit for x. Okay? That's what F prime is, or df dx. Whoa! Last slide. Let's see if there's one more. No, there's no more problem. So we are at the end of the section. Homework exercises here include either 5 or 7. Do 5. It's both at calcchat.com and at calcview.com. Do any of the odds 7 through 25, a whole bunch of them there. All of those are at CalcChat, 17's at CalcView. Do either 27 or 29, both at CalcChat, 27's at CalcView. Do any of the odds 31 to 37, they're all at CalcChat, 37's at CalcView. Do any of the odds 39 to 53, they're all at CalcChat, 43 is at CalcView. Do either 55 or 57, both at CalcChat, 55's at CalcView. Any of the odds 59 to 63, they're all at CalcChat, 59's at CalcView. do either 65 or 67 or both. They're both at Calc Chat. 65's at Calc View. You can explore the concept if you'd like. 69 or 71 should be at Calc Chat, and then 73 should be at Calc Chat. You can sketch a graph if you want to. 75, it should be at Calc Chat. Then finding equations of tangent lines, 77, horizontal tangent line, 79, and then another finding equation of a tangent line at 81. So I do at least one of 77 or 81, and probably, oh, there's more. 83 is a linear approximation, not a bad thing to look at. It should be at Calc Chat. There's some true faults there, 85 to 89. Don't expect to see very many of these on a test. However, good thing to think through to make sure you got your concepts right. Okay, they should be at Calc Chat as well. 91 or 93, either one of those, they're both at Calc Chat. 91's at Calc View. 95 should be at Calc Chat, and 97 also. Both of those are vertical motion, so do one or the other or both. 91, 99 you can think about doing if you want to. 101 is a volume problem. 103 is a modeling data problem, so you can do either of those if you choose. They should be at Calc Chat. 105 is a velocity problem. 107, finding an equation of a parabola, which, by the way, that quadratic equation would have given us one. 109 is another tangent line problem. And then 111 is sort of interesting. You can choose to do that or not. It should be at Calc Chat. And 103, the same type deal. 105, the Putnam Challenge, only if you're planning to do some of those advanced challenges, then knock yourself out. All right, let's go for 2.3. Let's end this one and go to 2.3. All right. Still in Chapter 2, differentiation. And 2.3 is product and quotient rules. And then we'll jump into higher order derivatives. I don't know why all these are grouped together, but I guess I had to group them somehow. So here we go. So first we'll find the derivative. Oh, remember how we did the sum and the difference rules? Derivative of a sum is the sum of the derivatives. The derivative of a difference is the difference of the derivative. Pretty straightforward, hopefully what you would be expecting. Don't expect that for products and differences. The derivative of a product is not the product of the derivative. Is not the product of a derivative. Actually, Leibniz blew this when he first wrote his paper. Remember, he was anxious to publish, and Newton was so tedious about wanting to make sure everything was exactly right before he published. So Leibniz jumped ahead and blew it. Okay, he found out the derivative of a product was not the product of the derivative. So we'll do the product rule, and then we'll find the quotient rules even worse. Okay, but not bad. Okay, we'll find the derivative of a trigonometric function. I think we've already sort of done that, haven't we? And then we'll move on to higher order derivatives of a function, which hopefully will be something that just makes perfect sense to you. So let's look at the product rule. As I said, you've learned that the sum, I hope you learned, that the sum of a derivative of the sum of two functions is simply the sum of the derivatives, and the rules for derivatives of products and quotients not as simple. So here's the product rule. And if I'm not mistaken, I have no idea why they have a vertical line there. It's not me, okay? And I'm pretty sure it's not in the book. No, okay? Typesetter blew something here. The product of two differentiable functions, first, f has to be differentiable, G has to be differentiable. The product of the two functions will be differentiable, but not probably like you would expect. Moreover, derivative of fg, that product of the two functions, is the first function times the derivative of the second plus the second function times the derivative of the first. Okay? Said a different way, derivative of a product of two functions is the first times the derivative of the second plus the second times the derivative of the first. Okay? Or you could say derivative of the first times the second. Either way. Now, I keep going back to my tutoring the Indian kid, and he threw me on this one too. Oops, let me get my pen back. If you write it this way, let's see. Say again? Yeah, that would be, maybe this one isn't quite as bad. F times dg dt plus g times d. Oh, wait. It's not t. If x is the independent variable, it's not a t. It's the x. Well, all right. Let me get that. Oops. Hit the wrong key. Okay. All right. Dx g times f dx. Or you can say, okay, this wasn't as bad. It's going to be the quotient rule. I'll tell you what he said. Any way you write it will be fine. Okay? First times derivative of the second plus the second times derivative of the first. Now, I'm sure there must be a proof for this. Oh, yes, there is. Okay? And it would sort of be fun if we had time to do the proof, to do those. But especially if you're going in the math as a field, it's a nice proof. Trick in the middle of it, but once you learn the trick, it makes perfect sense. Okay? So, product rule can be extended to cover products involving more than two factors. For example, if f, g, and h are all differentiable functions of x, then the derivative of the product of all three would be the derivative of the first times the product of the other two, plus plus the first times the derivative of the second times the product of the third, plus the product of the first two times the derivative of the second. So you just take a derivative of one of the functions, each one multiplied by the product of the other two, and keep going. So before they show us how to do just a product of two, they give us this one for 3. Okay? What would you guess that would be? Way before we've even done the product of 2, here's a product of 3. Give me a guess. Second? And that would be 2x times sine times cosine. That's the first term. Next. What's next? X squared times
Cosine squared.
derivative of cosine, which is cosine. So cosine times cosine, cosine squared. So the second term, or however you did it, x squared times cosine squared. Third term, okay. You said negative, and there's a reason for that, x squared times sine squared x. Because the derivative of cosine is minus sine. So that would give you minus x squared times sine squared. Okay. Now, and that's exactly what we said. Now they factored out the x squared. This is exactly or kind of what we said. They factored out the x squared from the last two terms and came up with this. Oh boy. Let's dial it back to trig. Anyone remember what this was? Trig identity. Oh!
That'd be a -1.
Nope. Almost a good try, but cosine squared plus sine squared would be 1. But cosine squared minus sine squared is not negative. Okay? It's a double angle formula. Anyone remember? Cosine 2x. Okay, that is the difference between those two. Cosine 2x. And actually, 2 times sine x cosine x is the sine of 2x. So this would be x times sine of 2x plus x squared times cosine 2x. Whoa! Strange, huh? But sort of true. We don't need, that's not really all that important at this point. Okay? Why they jumped off and said that before they even gave you one to do a simple one, I don't know. Okay? Now let's see. Derivative of a product of two functions is not in general given by the product of the derivatives of those two functions. Okay? We understood that. Leibniz blew it when he did it. Let's see. Before we go any further, they do give not an example, but sort of like an example. What if we have f of x is equal to 3x minus 2x squared, and g of x, is it going flashing in and out? That's when you're thinking too hard. Never mind. Okay. 5 plus 4x. Okay. Okay. We haven't done example 1 yet. What would be derivative of f of x? Oops. F prime of x. Say again? 3 minus 4x. And what's the derivative of g prime? 4. Okay. If you multiplied those two together, that would give you 12 minus 16x. Don't do that, okay? Unless that's really what you're looking for. This isn't the derivative of the product. But what they're saying, with that in mind, let's do example 1. Find the derivative of h of x, which is the product of those two functions. So what is h prime of x? And it doesn't matter which order you give me these things. Either which one you do derivative of, which one you write first, none of that matters as long as you do it right. Okay? So what would you do? What would this be?
3 minus 4x.
3 minus 4x, that's the derivative of the first.
Times 5 plus 4x.
5 plus 4x, that is the second one. Plus 4. Okay, he's doing derivative of the second. 3x minus 2x squared. All right. First product, good old foiling would give you, help me, 15
minus 20x
okay, plus 12x
minus 8x
minus 8x
minus 16x squared.
minus 16x squared plus 12x
8x squared.
minus 8x squared. Okay, combining like terms here, what do we get? 15 is the only constant I see. Next,
4x
plus 4x
minus 24x squared.
minus 24x squared. Nowhere close to what we got as the product of the derivatives. Don't even think of that. This is how you do it. First times the derivative of the second plus the second times the derivative of the first, or whichever order you want to do this. Just remember you got to do one step at a time. Let's see how they wrote it in descending order of powers, which is perfectly fine, and they still got the right answer. Good for them. So any questions before I show you how they did it? Everybody see it? Okay. Now, just like you did, they do first times the derivative of the second, plus second times the derivative of the first. I think that's pretty, well, close to what we did, okay? Yeah, we did them in reverse order, but that's fine. So that gives you first times the root of the second, which would be times 4, plus the second, which would be 5x plus 4, times the root of the first, which is 3 minus 4x. Perfect. That's 12 minus 8x squared plus 15 plus minus 8x minus 16 x squared. And that was minus 24x squared plus 4x plus 15. If you want to write it in descending order of powers, which is sort of standard, but it's not necessary. Any questions? That's the product rule. Now the quotient rule. SpaghettiOs. All right, quotient rule. Quotient f of g of two differentiable functions, f and g. They both have to be differential, otherwise you can't do a quotient, okay? Is self, the quotient of two differentiable functions, is differentiable at all values for x except where g of x equals 0. Of course g of x can't be 0. That doesn't make a quotient you can calculate, right? You can't divide by 0, okay? So as long as g of x is not 0, you can take its derivative. Moreover, the derivative f divided by g is given by the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the square of the denominator. This is the one that when my Indian friend said it, I went, what? Okay, here's how he said it, okay? I'll write g of x times df dx, okay, minus f of x times dg dx over g of x squared. I would have said g squared of x, but this is how to do it. Okay, except he didn't call them f and g. He did them highs and lows, okay? And this is how it came out, only much faster than I can speak. Low d high minus high d low over low low, okay? And that's really not a bad way to remember. Start low, okay? Low d high minus high d low over low low, okay? That's the easiest way I can think of remembering it, where low means the denominator, high meaning the numerator, okay? Start low. And the reason for that, when you take, and we'll see this later, when we take the derivative of the denominator, it's always going to be a minus. Okay? So that's where that. So you have to start with the denominator, then the derivative of the numerator, minus the numerator times the derivative of the denominator, which gave you that minus sign, and then the denominator squared. Okay? If that's helpful to you, I found it confusing at first, and then I realized what he was saying. So, oh yeah, that's a pretty easy way to remember. Okay? Any questions? All right, so let's find the derivative of y. In other words, y prime. What would that be? You tell me. Where would you start? Anybody? X squared plus 1, that's your low, times 5, that's d high, minus 5x minus 2, 2x, all right, that's it. Oh, well, we can clean it up a little. What would that be? Please clean it up a little. Distribute, huh? A little louder. 5x squared plus 5 minus 10x plus 10x squared 4x plus 4x over. Don't multiply that one out. Just leave that as x squared plus 1 squared.
It's 10x squared minus 4x.
Is it? Minus a minus is a plus, okay? Yeah, those signs are going to be the thing that trip you up the most. And this one has a minus in it in addition to any that may be inside of it. Does everybody see why that has to be? It's a minus 5 times this and a minus 2, which is 2 times that. Okay. So that does come out a plus at the end. So what does this do when you combine like terms? Negative 5x squared plus 4x plus 5 over x squared plus 1 squared. Now, usually at this point, I stop and see if I can factor this in any way. If I can, and any one of them has a common factor down here, yeah, we can eliminate it. I don't think anything's going to work for you there. So I think we could just leave it like that. Let's see if we can. Oh my goodness, we skipped example 2, didn't we? Let's back up. Oh, we skipped example 2 and 3. Let's just check our answer here. And sorry about that. So let me clear this out of the way. Anyone need it longer? Okay. And low D high minus high D low over low low is that, exactly like we got. And they didn't factor it either, okay, because it's not factorable, I don't think. Okay, so let's back up. Sorry, I forgot this. Let's do examples 2 and 3 before we move on past 4. Find the derivative of y is equal to, 3x squared times the sine of x. What is dy dx, or y prime? A little louder. 6x times sine x, perfect. Is that all? Plus a little louder, I can't hear. First is 3x squared. And what's the derivative of sine? Cosine x. All right, that should be our answer. Now, last time they factored common factors out, so let's see if we did that. That would be a 3x times 2 sine x plus x cosine x. I see no reason to do it, but let's see how they did it. Oh, they did it again, didn't they? 3x times, they reverse the order, x cosine x plus 2 sine x. Of course, it doesn't matter what order you write them, as long as you write them correctly. But of course, if you were doing WebAssign, and you wrote it this way, or wrote it this way, and they wanted it the other way, they say wrong answer. When it's not a wrong answer, it's just not the way they wanted you to write it, but there's no reason to expect this is better than that, or vice versa. Okay. Let's do example 3. And by the way, I can't remember. I've got to check. I think they may have sent finally the code for this class. I started working on that this morning, but didn't get that far down the email to see if they had sent. I think I told you for my Math 113 class, they gave me problems from intermediate algebra for them to work on. So they had to go back and redo those. Not done yet. So, but I think they may have done this one. So let's clear this and see what we get for example 3. Find the derivative of y is equal to 2x cosine x minus 2 sine x. Wait a minute, can you do that? Sure you can. Okay. What's second? Okay, that is one good thing to do. I don't think they suggest it, but let's take out a 2, and that gives you
x cosine x minus sine x. Okay? Now, since you're taking a derivative, remember a constant times what are you taking derivative? Just a constant times the derivative. So y prime is going to be also have that 2 in front. And now let's take a derivative of what's inside there. And what will that be? Cosine x will be a good first term here because you take the derivative of the first, and that's 1 times cosine x. Next. My stomach's growling, sorry. Help me. Minus what? X sine x. Very good. It's the you did the derivative of the first times the second plus the first times derivative of the second. The derivative of the second is a negative, so that would be a minus x sine x. And then next, help me. Somebody help. I'm drowning up here. You told me to write it down, didn't you? What you said? Oh, okay. All right. We did the derivative of the first times the second. That was that, right? Plus the first times derivative of the second, right? Right? This is a product rule. It has 2 pieces. Now we're doing the difference rule, which just is take the derivative of the second. And what's that? What is the derivative of sine? Cosine x. Oh my goodness, look what happens. Cosine x's add to 0, don't they? So we're left with 2 minus 2x sine x. And that's all they got to. Everybody see that? First term is a product rule. Second term, you just take the derivative of that. Product rule will have 2 pieces. The next part just has 1 piece. Derivative of sine x, negative sine x. Make sense? All right, good deal. Go. We went back and called 2 and 3. Oh, and we talked about what the quotient rule is. They did have a proof there, and this is even a little more messy than the proof of the derivative of the product rule. It's a pretty decent little proof. Okay? So there was example 4 we've already done. So let's move on to, that's what we got for 4. Ooh, they're not doing 5 or 6 or 7. Okay. So let's go back and do 5, 6, and 7. All right. And guess what, team? I forgot to bring my watch up again. I always do it first thing in the morning. I was in a rush. Okay. So y'all will let me know, won't you? Y'all are so kind. So kind. Okay. So, example 5. Find an equation of the tangent line to the graph of f of x is equal to 3 minus 1 over x plus 5 at negative 1, 1. So we're looking for the equation of a tangent line. Okay, that's what we're looking for. It'll come back. All right. One thing I recommend first, always check and make sure it makes sense. Okay? And what I mean by that is that point even on this curve. If it isn't, you're going to have a hard time coming up with the equation of a tangent line. So I'm a cynic, so I always check. And how would I check that? Yeah, put -1 in for x, okay? So that'd be 3 minus 1 over -1 would be -1. So 3 minus 1 would be 3 plus 1, which is 4 over 4. Yes, 1 is the answer. Yes. Now I'm happy to go on and proceed, okay? But what would you do before you proceeded? That's a little awkward looking, isn't it? Say again?
You should multiply by x.
Multiply the numerator by x. Is that what you're saying? Okay. Oh, and the denominator. I like that idea too. Multiply the numerator by x and the denominator by x. This form is one example of what usually algebra books call complex fractions. I don't like that term because complex usually mean imaginary numbers are involved. They're none. I like to call them complicated fractions. But of course students say, well, all fractions are complicated. No, they don't say that, do they? Okay, so I guess we have to call them complex fractions. What does that give you? And why can we do this? Why can we multiply by x over x? I understand why we're doing it there. Well, why is that a legal thing to do? You just can't go around multiplying by anything you want to, can you? Yeah, because x over x is 1. And when can you multiply by 1? Anytime you want to. So that's not going to change the value, just change how it looks. So what would this be? Numerator, 3x minus 1 over x squared plus 5x. All right. There's our new f of x. It's the same f of x. It's just in a little bit nicer looking form. How are we going to find? Oh, okay. We're looking for the equation of a tangent line. What do we need to know the equation of a line? Second? All right. What will the derivative give you? Slope. And that's what you need to know the equation of a line. You need 2 pieces of information. 2 points will give it to you, a slope and the intercept will give it to you, or the point and a slope will give it to you. We already got a point, and we already verified it was on that line. All we need now is to get the slope, which would be take the derivative of this, which is a good thing to do. F prime of x will be what? You tell me. Say again? Say that again. X squared plus 5x, the low, x squared plus 5x, times 3, that's d high, minus 3x minus 1, that's high, 2x plus 5, that's d low, all over x squared plus 5x squared. There's your low. Okay? Now what do we do? That's a mess. Well, let's clean up the mess a little bit. What will that numerator become? Help me. 3x squared. Next. Plus 15x. Ooh, now we got some foiling to do. Minus 6x squared minus 15x plus 2x, so that would be minus 13x, right? Yay or nay? And this will be a plus 5, you said? I thought you did. Okay. Is that right? Okay. Now, if it looks like I'm rushing, I kind of am. We're running out of time. Also, I don't have a lot of space, so I'm just trying to do many steps. Please, folks, take as many steps as you need doing these problems. Don't try to push them. Don't rush them, because you'll see I make mistakes, by rushing. Is that okay? I still can't hear you. The 13x. You're not sure about that? Here we had a a plus 15x with a minus sign in front of it, so that gave you a minus 15x. Then you had a minus 2x, but a minus sign in front of that would be a plus 2x. I think that gives you minus 13x, right? Again, I'm skipping steps, so don't skip steps if you can't tell where they're heading, okay? You'll fall down the stairs, okay? And that's all over x squared plus 5x squared. Now we can combine some like terms here. What would that be? Minus 3x squared plus 2x plus 5 over x squared plus 5x squared. Okay, that gave us our derivative finally. What a mess. Nicer mess than we had before. But what do we do with it? Why do it anyway? Say again?
Plug the point in.
And what point do you put in there?
-1.
Yes, x equal minus 1. You don't plug the whole point in, just the x value, okay? So f prime at -1 would then be minus, help me, 3 minus 2 plus 5. Oh my, I think we can stop there, can't we? What will that give you? 0. I don't have to mess with the rest of it. That's a 0. Blah, blah, blah equals 0. Okay? First derivative is 0. Okay? What does that tell you?
Slope is 0.
Slope is 0. All right? But how can that give us an equation of a line? Equation of a line is y is equal to, or y minus y1 is equal to m times x minus x1. We're running out of time, so I went ahead and did that. What's your y1? 1 equal 0. So guess what your equation is? Y equal 1, or y is equal to 1. That 1 there. There it is. Could it be that easy? Let's see. My goodness, it is. Okay? Thank you for giving us such an easy point to do. Okay? Don't let that throw you. A slope of 0 means you have a constant value. Y is equal to 1. If it's equal to 1 there, it's equal to 1 everywhere. Okay. Make sense? Most of the time you're going to have more work to do. Okay? I'll promise you that. Okay? In fact, that denominator would have been 1 minus 5 is 4 squared is 16. So if it had been, yeah. But we didn't need to do that because the numerator was 0. Any questions on that? Everybody see it? How are we doing time-wise now?
19.
Second? 19. And we're going to 40, right? We got plenty of time. Okay. So let's erase all the ink. I shouldn't have been rushing so much, should I? Okay. Goodness, I can't get it to go. All right. Let's do example 6. All right. All right. 4 parts to 6. Okay. Here's a function. Y is equal to x squared plus 3x over 6. Okay? Now, if what we were asked to do is find its derivative, what would be the easy way to do that? How many vote for quotient rule? Good people. Good people. Why didn't you vote for quotient rule? So yeah, the derivative of the quotient will be 0. We don't need to do that. All we have to do is factor out a 1/6. And that would be, what's left? X squared plus 3x. That's a lot easier to take a derivative of than a quotient rule. So what would be your y prime? 1/6 stays 1/6. What's left? 2x plus 3. Now, if you wanted to, you could multiply that back through. I don't know why you would want to, but you could. That would give you 1/3 x plus 1/2, if you insisted. But there's no reason to. You could write it back like they had originally. That would have been a 2x plus 3 over 6. That's a perfectly, all three of these are perfectly correct, absolutely fine answers. There's nothing wrong with any one of them. They're all three correct. All right. That was the A part. How about B part? What if you have y is equal to, it'll come back, 5x fourth over 8. Quotient rule? Please not, okay? Rewrite this as 5/8 times x to the fourth. Now take your y prime. And what would that be?
5/8 times 4 to the x cubed.
Okay, 5/8 times 4x cubed. Can you do anything to simplify that? Four will go into 8 twice. So that can be 5/2 x cubed, or writing it back in a form like they had to begin with is 5x cubed over 2. Nothing any better about that last way. In fact, this time they left it as 5/2. They left it in this form. I can't make any sense out of what how they get their final answer. They're not really being very consistent. All of them are good answers. They all work. Wrong answers don't work though, so don't give me that. All right, I'm going to have to erase them. Anyone need this before I erase? Everybody got it? Okay. So let's go back and do C and D. First C, y is equal to -3 times 3x minus 2x squared over 7x. And how would you want to start out? Second? Okay. Actually, an excellent idea. Excellent idea. Okay. So let's see what we got there. -3x times 3 minus 2x, right, over 7x. And now what can we do? Divide out the x's, okay? And that would be -3/7 times 3 minus 2x. Now, I'm not sure there's really a huge advantage of factoring that out. So it may be, it doesn't matter. What's your y prime then of that? A little louder.
It would be -3/7 times -2.
Okay, -3/7 times -2. Is that what you said? Okay, that would be +6/7, right? Can it be that easy? Yes. Okay. Good catch on the fact there was a common factor of x. Okay. I think we would have seen it earlier. Based on what we were doing, I was thinking, let's get the -3/7 out of there and see what's left. And once we had done that, then we say, hey, yeah, but now we can factor out an x. But you saw it from the very beginning. So yeah, that made the whole problem a lot easier. Does everybody see that? Any questions? All right. How about this last one now? Y is equal to 9 over 5x squared. What would you do first? Anybody have any suggestions?
X squared up, making an x to the -2.
Oh, I like that way of thinking. I'm going to also do 9/5 times x to the -2. Before, we'd have to use a quotient rule, which we all know and love, but this way we use a power rule, which is so much simpler, and that would be what? Oh, well, let's see. Y prime then would be what? Help me. Maybe it's simpler, I don't know. Minus 18/5. Okay, and then if you wanted to go back and put the x in the denominator, that is doable. Be a minus 18 over 5x cubed. Okay, that's exactly what they got. Good deal. In my mind, always power rules are so much easier than quotient rules. So don't even mess with the quotient rule if you can help it. If there's no way around it, yeah, you're stuck with it. But if there's any way you can manipulate your problem to not have to remember low D high minus high D low, all that mess, then it's usually easier to do it without it. All right, any questions? But if you're hard workers, okay, you can do it the hard way. Catch you. All right, I think there's one more. That's example 7. Y'all gonna keep me straight now, right? What's that? 10 minutes, good. All right, example 7. I think we just did this, didn't we? Okay. If n is a negative integer, then there exists a positive integer k such that n is equal to negative k. Wow, why didn't I think of that? Okay. So by the quotient rule, why would you want to do the quotient rule here? Can we just not do the quotient rule here and do derivative? If, let's see, they don't even tell you where to start. It says d by dx of x to the n just do it, okay? Even if n is negative, like we just did, that would be what? By power rule. N times n minus 1. And if n happens to be negative, fine. It's still that answer, okay? So why do a quotient rule on it? I don't know. But if you need to do that to convince yourself it's right, knock yourself out, okay? I just see no reason to even fiddle with that, okay? Now, let's move on to derivatives of trig functions. And I was thinking we've already done this, but maybe we do need to do some more. Oh, yes. We only did derivatives of sines and cosines, didn't we? Ha! Silly me. Let's do the other trig functions. So knowing the derivative of the sine and cosine function, you can use the quotient rule, yay, to find the derivatives of the 4 remaining trig functions. Okay? Now this one I think is worth a do here. Okay? Just so you don't have to memorize these things. So after you use them a lot, you know them by name, so you know it. But a tangent is what? What is tangent? It's sine x over cosine x. Okay? And derivative of a quotient is what? Low, which is cosine x. times derivative of sine, which is cosine x. So that's cosine squared x minus sine x times a minus sine x. So that's sine squared x. Oh my word, that's pretty simple, isn't it? Over cosine squared x. Well, what's sine squared x plus cosine squared x? 1. 1 over cosine squared x. And what is 1 over cosine x? Second? Okay, yeah, we could do that, but let's not. That's way too much work. I'm too lazy for that one. What is 1 over cosine? Secant. So this is secant squared x. So if you ever forget it, it's easy to get. Okay? Derivative of the tangent is secant squared. Okay? Now, derivative for a cotangent. What's the derivative of the sine? Cosine. What's the derivative of cosine? Negative sine. Okay? Well, guess what? Your cos, derivatives of cos are negative. It happens here, it happens there, it happens there. I don't know why, I mean, it does. It just happens. So, derivative of cotangent would be the opposite of the reciprocal function of, I mean, not reciprocal, the cofunction of secant. So it would be minus cosecant squared x. So I won't go through and do that one again. But now derivative of secant x. What is secant, by the way? 1 over cosine. Yeah, we just said that, didn't we? Okay. So what would that be on? I think we probably use quotient rule rather than power rule because power rule doesn't work as well with sines and cosines. So let's do quotient rule. What would that be? What would it be? Low, which is cosine x, d high, which would be 0. Phew, that's good. Minus times minus sine x. Oops, that's not 6. Okay, sine x. So that would be sine x over cosine squared x. So that would be a sine x over cosine x times 1 over cosine x, wouldn't it? Cosine squared is cosine times cosine. And what is sine over cosine? And what's 1 over cosine? So secant x tangent x. Really bizarre. Derivative of secant is itself times something else. Okay, it's weird. And cosecant would be minus cosecant times cotangent. All cos over there, except for sine and cosine, they don't count. But for these four, your functions have only functions, and your cofunctions have only cofunctions for the derivative. Okay. Got it? You don't have to, you can do whatever you want to. You can dot memorize and derive, that's pretty easy to do, or just learn them. Get to use them often enough, and you'll get to know them. Okay. And they just did 1, we did 2. Okay. So, example 8. Here's our function. Y is equal to, I hate this when we do this. Y is equal to x minus sine, or tangent x. What is its derivative? 1 minus secant squared x. Okay. Now we could have taken that a little further, couldn't we? What is 1 minus secant squared x? Anyone remember that? Okay. Let's go back to the easy one. Sine squared x plus cosine squared x is equal to 1. Okay, let's divide both sides by cosine squared x. every term on both sides by cosine squared x. Legal in most states, right? Just not where cosine is equal to 0, but we'll throw those out anyway, okay? What does this give you? Tangent squared x plus 1 equal secant squared x. Y'all remember that, didn't you? Okay. Now, if you want to subtract the secant squared x from both sides, that would give you minus secant squared x minus secant squared x. And let's get rid of the tangent by subtracting tangent squared x from both sides. So that goes away, those go away. So 1 minus secant squared x would be minus tangent squared x. Don't try to memorize that as a thing. This just showed up here, but that was a slightly simpler way to write it. We had to do so much work to get there. Easier to just leave it like that, okay? But that is minus tangent squared x, right? Let me erase that. I have a feeling they're going to give you too much information here. So let's do this. All right. What would that be? Derivative of that. What rule do we use? Product rule. How does that go? X
times secant x times tangent x.
Okay, times secant x tangent x
Plus
secant
x
times 1. Okay. Plus secant
x.
x. Oh, excuse me, I got hiccups. And on this one, if you wanted to, I don't know if you wanted to or not, you could factor out a secant x. Okay, and that leaves you x tangent x plus 1. Okay, nothing much you can do with that. I don't know, did they do that or not? I don't think they did they? Yes, they did, didn't they? Whoa, there it is. Secant x times 1 plus x tangent x. I said tangent x plus 1. Doesn't matter what order. Unless you're doing WebAssign. Okay. All right, good deal. Any questions on that? Okay, I hear zipping. What does that mean? We are out of time. How sad, wipe those grins off your faces. Okay. All right, we'll pick up and go from example 9 next time. However, good news is we got far enough along to get some homework exercises. Any of the odds 5 through 9, they're all at Calc Chat. 5's at Calc View. Any of the odds 11 through 15, they're both all at Calc Chat. 11's at Calc View. Any of the odds 17 to 21, they're all at Calc Chat. 21's at Calc View. Any of the odds 23 to 27, they're all at Calc Chat. 23's at Calc View. I think you can do any of the odds 29 to 39, they're all at Calc Chat. I think you can do any of the odds 41 to 55, they're all at Calc Chat. 41's at Calc View. And then you can use technology if you want to with 57. Slope of the graph, 59 or 61, they're both at Calc Chat. Equation of a tangent line, we were doing that. Those are 63 through 67, all at Calc Chat. And 69 or 71, they're both at Calc Chat. We'll stop there and pick up the rest of those later, since we're losing half the class anyway. All right, good deal.